In tonight's omarvision tutorial, I'm going to go over how to do the MarchingCubes algorithm in Unity. Here I have a sample project, and in this project I'm using the MarchingCubes algorithm. Let me press play. So basically what the MarchingCubes algorithm does is it divides up a volume of 3D space with a bunch of points. So the points are evenly spaced apart, kind of like a grid of points in 3D, and anywhere that the points are on or off, it takes a look cube by cube of the space and sees what faces, if any, should be rendered into a mesh. And it goes cube by cube. So you could think of it as a sampling of 3D space going cube by cube and then making some mesh triangles to wrap that space up. So here, this code is running, and here is a ball that I'm going to use. The ball is going to move through the 3D space, and whatever points it collides with, the points are going to turn on. They're going to turn red. So here I'm moving into the 3D space, and everywhere the ball touches, the points turn red. And then I'll just come out right there. Okay, so now if you look, the ball moved through this 3D space, and the places where it touched, the points turned on, and the other points are off. Now what the MarchingCubes algorithm will do, I'm going to do it in slow motion. It's going to go through the space and try to wrap the on points to be the inside of a mesh. So let me just press the slow button here. And what's happening is it's going cube by cube through the space. And when it gets to the ones that have something to render, it's going to actually figure out some faces. You see, and it puts the faces together, kind of like a jigsaw puzzle. Okay, so what it's looking for is the places where there's a difference between a point on and a point off, and it just renders a mesh around that space. Okay, there we go. And then the rest of it is clear. It's just going to finish checking the volume until it gets to the end. So this ball went through, and all the points that were red, they're inside this mesh, and the points that are white are points that are off. See? So it kind of made a mesh. So I could do this in real time. Let me just check this thing, listen to the point event. So what I did was for each of these points, I have a trigger event that happens, and when the trigger event happens, it recalculates the mesh instantly. All right, so let me do it a little bit more. Let's move this ball. Maybe, I'll just move back here. And let me just move it in, and you can see that the mesh is getting drawn in real time. Let me just rub it around a little bit. It's almost like having a pencil and drawing in 3D instead of drawing in 2D. Like that, wherever I rub, the mesh just grows. Okay. So the thing is every time I move around and a point changes its value, the cube thing that you saw happen slowly, it's happening in an instant, and the mesh updates itself. And you can see that the whole mesh, let me just see here. I'll just spin around it a little bit so you can see all the sides. All right, the only points, and the points on the inside, they're the red points, and the points on the outside, they're the white ones. Okay, so this was an example where I could like draw with a ball, but you know, you don't have to draw with a ball, even though I thought that was the coolest thing. I could also just do noise in 2 dimensions. This is like hills, and it could show something like this. Let me move this ball out of the way. Kind of drew something. And then also in this tutorial, I figured out how to do Perler Noise in 3 dimensions. It's just a little adjustment to the Perler Noise 2D function that I could do it in 3 dimensions. So let me do some noise in 3D, and then let me show you that. So when I do the Perler Noise in 3 dimension, basically it kind of like makes caves, you know? We'll make empty vacuum spaces inside and out. So this is how it looks. So the thing that was the hardest for me to figure out were the configurations for the cube. So right now I have this cube here. Let me turn on the gizmos. All right, because I think if I get really close to the cube, every cube I consider it like a point A, B, C, D, E, F, G, H, and right here all the points are red. So there's no difference in the values of the points here. They're all on. So there's no faces to make for this cube, and therefore it didn't. But let me move the cube to a different location. Like maybe is it here? Where I have something different in a cube, and I move my cube right out of the volume of space. Okay, I have to use the shift key, and I go down. All right, so here we have a cube where A and B is on, C and D are off, E and F are on, and G is off and H is on. So what happened, you see here, is that for this one cube, when it sampled that space, it made these faces. It's basically separating there's always a point for a triangle that's being drawn that's separating an on spot from an off spot, okay? And all the points on the other side are the other on spots to the off spots. And it does this for every cube space. So as you can see, a cube has 8 points, and the values could either be on or off. So since there's on or off values, that's 2. And since there's 8 points, that's to the power of 8, which equals 256 different ways that the points could be on and off. So for each one of those ways, I have to have something that tells my code how to render the faces. So this is what I'm going to show you next is something I wrote to figure that out. I know that somewhere on the internet they probably have it, that there's an array or something like that, but just so I could show you the complexity of the 3 weeks I took to figure out the configurations myself, because I just wanted to do it the hard way instead of just getting the array from the internet. This is a little program, this scene over here I wrote to help me figure that out. So here is a cube, and can I just get this to focus, please? Thank you. This is a cube, all right? And right now there's no points on, but over here it's going to show me the configuration. So on configuration 0, all the points are off, therefore all the bit positions here are off. But when I go to 1, point A is on, so out of the 8 points, A is on, and that equals 1. All right, so if the first position of this binary representation here is on, then that equals 1. That's 2 to the power of 0 equals 1. And for that, I just have to draw one triangle to separate the on from the off. Oh, no, Cruz, I'm working. Stop. I have this big dog, and he keeps wanting me to pet him every time I'm working on the computer. All right, so let's see. We got other configurations. Sometimes there's 2 points on, and that's easy. For this one, I just need to make 2 triangles, basically, to separate the on from the off. And we got another triangle. Let's see. This one's a little bit more complicated. I had a triangle, a corner point on, and another corner point on. And then in between here, I just separated because these 2 are on. So basically what I started finding out was that there's like a rule that I had to follow to make sure that I drew enough faces. Everywhere on these lines, you see this is where I'm making my points for the triangles. I make them on the halfway marks. So if there's an on and an off, let me just turn off the gizmos so you can see the color. If there's an on and an off, I must have a point for a mesh triangle, okay? So for all of these, there should be a point for a mesh triangle. But if there's anywhere where the 2 corners are the same color, I better not have a mesh triangle. And this is what I kind of went through for about a week, trying to figure out all 256 configurations to see if they were right. And a way that I was able to see, well, a proof that my configuration was wrong would be when I go to the example scene and I kind of like would draw around with that ball in 3D. If I had a hole in the mesh where I could see into it, then some configuration was wrong. But I think now that I have all 256 correct, so if you use my code here, if you use this MarchingCube script here, this has the correct configurations. But, you know, I basically went through like this for all 256, and with this scene code here, I could actually see what the configurations look like. All right? And let's see if I can see show you some of the weirder ones. This one's kind of weird, you know, because it was like 3 corners were on. So I just connected 3 corners with a mesh. And this is one thing you have to remember to do is when you're drawing the triangles for a configuration of the cube, you have to draw them in a clockwise order. You have to connect them in a clockwise order on your triangles array in the mesh. And that tells Unity which side to draw. Okay, so that kind of helped me too, because I could just turn this cube around to face me with the red on the other side, and then I could figure out the clockwise order of the points. So that was a weird configuration there. And this one, there's 256. Now, if I could just kind of click through a bunch of them a little quicker and see if there's any other weird ones. But, you know, if you download this project, you could click through and look at all the different configurations yourself, too. So also, I was like looking around on the internet if there was something that showed every configuration. And I think that the configurations repeat themselves in the 256, but sometimes they're rotated around differently, you know, around different points. But this one was a weird one, too. I hope they're right, because these I kind of figured out myself. And that goes through like that. So anyway, what I want to show you is how to use the script I made, this MarchingCube script, so that you could use a script and implement the MarchingCube's algorithm yourself. So let me stop this project and close it, and I'm going to open up a new project and start a new project with you guys and girls to make a brand new MarchingCube program. So here we go. It's going to be a 3D project, so I'll call it MarchingCube cube light, because it's just going to be the bare minimum to get a marching cube thing rendered, not with all the stuff that you just saw where I had all that fancy cubes highlighted and moving around. All right, so I'm going to call it Marching Cube Light 3D project create, and I'll let Unity create the project. And I'm using Unity 2020, but that shouldn't make a difference. There's nothing in the code that's really dependent on the version of Unity. But one thing I noticed is with Unity 2020, I mean, I don't know, it seems like everything takes longer to import and start. Maybe it's just me. You guys tell me if you think it's taken longer in 2020 than it did in 2019. All right, so here I have a brand new project. So I said that the first thing was to get my Marching Cube script. So that is going to be for this video. If you go to omarvision.com/tutorials, that I'll have the script there. I'll have the whole project there, both of them. So I have the Marching Cube script. Let me just drag and drop it into my project. And let me show you what is inside this script. Okay, so let's open this up. Got Visual Studio 2019. Okay, and here we are. Here's a script. So there's some required things when you're using the script, like the way you saw that volume of space. I visually was showing the grid points. They don't have to be visual, but I did need some kind of a grid point script to say if where the point was, a vector 3 for the position of the point, and a what else? And to say if the point is on or off, because it's knowing if the points are on or off how I could tell what the cube configuration is. Okay, so that brings us to requirement number 2. I need to make a grid of grid points. And then requirement number 3 is before I call any of the methods of this Marching Cubes class that I kind of wrote here, it's a static class, so you don't have to instantiate it. You just call MarchingCube dot da 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 da. So this class has all the Marching Cube functions. But before you call any of the methods here, it's depending on, it wants to know what were the points for the current cube. So before you call this Marching Cube thing that I wrote, you must, well, everything's moving around, define points A through H, okay, in this static class points that my Marching Cube class uses. All right, let me try to organize here a little bit. So, you know, points, there's a lot of points in a cube. There's the corners, there's the halfway points. But for every grid point, like I said, you need at least a simple class like this. You could use this grid point class if you want, or you can make your own. But here in the Marching Cube thing, it's using something called grid point. And like I said, it just has to have 2 properties, like the position and the on and off value of each point. Okay, so simple grid point, just make an array of these for the grid points. Okay, then for me to be able to think about all these points on a cube moving all over the place, first I made the static class for points. Okay, and this is a little visual representation of a cube. Okay, so you got the A, B, C, D, E, F, G, H. These are where these corners are. So each of those corners, it's wanting to know for the current cube what's A, B, C, D, E, F, G, and H. So this is where you could say points.A equals, you know, whatever your current cube is. And then here's the halfway points, which these are the halfway points on the between the corners. And you could do it as AB or BA, you know, it doesn't matter which way you put the letters, but these are all lowercase, the between the point corners, okay? And you just have to worry about setting the value of these before you call Marching Cube. Then, like I said, like you saw, the configurations are basically, it's basically like a byte, okay? So for each corner, it's a position in the byte. So A is the first position, or position 2 to the power 0, all the way up to H, which is 2 to the power of 8. Okay, so you got those here, power of 0, 1, 2, 3, 4, 5, 6, 7. So right here, this bits thing, it's just the easy way for me to say bits.a, and I get the right bit set in the byte. So I just reference bits.a, and it's like the value that represents that position. Then also to show the, if you wanted to see what it looks like, this little binary form function converts the config value, that number, and it kind of converts it into a string. So you can see if A was on, B, C, D, E, F, like you saw in the example. And this here is to see if a particular bit is set in the config number. Okay? And this letter is like, which position are you checking? Are you checking to see if the A corner is on, the B, C, D for the cube config? So I made this little helper class here. And then, you know, for any mesh, you have to set the UV coordinates. This is the easy way to think of the UV coordinates. UV coordinates, they're like how you're going to draw the texture on the mesh. So you draw the texture on the mesh triangle by triangle. So you think of a picture, it's a 2D thing. It only has A, B, C, D. So if you have your triangle for every point in the triangle, you just say, where are you going to get your picture from? And this just helps you. So if I'm getting it from point A, that's 0, 1. B is 1, 1, and it's like this. So this is the percentages, where in the picture, what percentage of the picture. So anyway, this is a helper class for that. And then finally, I get down to the actual Marching Cube class. So the grid of points, the Marching Cube class is going to hold your grid of points. The Marching Cube class is going to hold the values for the vertices, triangles, and UV that you are going to set the Unity mesh filter mesh to. So here I could get it all set up in these arrays here, and then boom, throw it to the Unity mesh to display itself. Then these are just some functions that you probably need. So, clear, it just clears whatever data you have for your vertices, triangles, and UV. Marching cubes, this actually marches the cubes, all right? If you call march cubes, then it's going to go through. First it clears, and then it goes through every cube in your volume of grid points, okay? It just uses the length from the three-dimensional array here to go through every point, z, y, and x. And like I said, first things first, you got to set the points, A, B, C, D, E, F, G. You got to set what the points are. So from the grid, since the grid's three-dimensional, you have the x, the y, and the z coordinate of the point. And then you call getCubeConfig. That just checks to see which points are on and off, and based on that, it sets a byte, or it sets a number, okay? And then I pass that number to the isofaces. This function is the one that took me, oh my goodness, it took me so long to get right, all right? Before I go into this, the getCubeConfig, right? It's going to check the points. So this is the getCubeConfig right here. So first I, initialize it to 0, the config value that's going to return. Then for each corner, for each point corner that the person defined, I check if that point is on or off, okay? So this little notation here with a question mark and a, yeah, this is a colon, and this is a semicolon. With a question mark and a colon, it basically, okay, point on. This is a true or false. Point on. If it's true, then I add bit A to my config number. If it's false, then I don't add anything. So when I go through down the line, each position, each binary position in config is either going to be set on or off. And I just return the number. Okay, so that wasn't too bad. That's what getCubeConfig does. It makes that number that represents which points are on or off. Then in isofaces, here we go. This is the important golden information, folks. This function is the one that takes that config value and decides what triangles to draw for that cube in the grid. All right. Then I just mentioned here, 2 to the 8, 256 configurations. So, woo, if I scroll, there's going to be a long list. And connect the points in a clockwise direction, so the on corners are inside the mesh. And 3, the off corners should always be separated by a triangle corner. And same side corners should not have a separated triangle corner. These are just some of the sanity check rules that I had to keep thinking of when I was seeing what triangles to make for each config. So it's a lot of code. So first thing I wanted to do is just set the vertices array. All right, so when I'm coming in to do the isofaces for the current cube, I just check how many vertices I'm starting off with in the beginning. How many vertices are already in my vertices array? That's my before count. So then after I come through this config function, I could have an after count. Just remember that. Okay, so here we go. We switch based on the config. So 0 means there's no points on. There's nothing to do. Don't add anything. A means there's that one corner on. I had to make one triangle. If you can remember the cube configurator scene that I was showing you where I was, saying next, 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 or previous, previous, previous. And I go through literally 256 configurations of which corners are on. And I figured out the vertices to add, and I add them kind of like in a clockwise order for each. So everything here is a multiple of 3 because it takes 3 vertices to make a triangle, and I'm having every triangle have its own vertices defined. So if you ever look in a list here for 9, this is a multiple of 3. It's always a multiple of 3. 3, 3, 3 for every triangle. This is 2 triangles here for config 10 where D and B are on. And this goes on and on. All right, and on and on. Yeah, this took me a long time to get this set right. So this is literally the gold. Now it's not really optimized, I guess you could say, because I'm adding a vertice for every single triangle. But I don't know, maybe that is the fastest way, or maybe there's a faster way if I don't make a vertice for every triangle's corner. But keeping it simple and just trying to understand stuff, that was my goal here. So I just did that, and this goes on and on and on and on. So I don't want to type this every time I do a game where I'm going to do marching cubes, and I'm almost to the end here, 228. So remember, 0 had nothing to add for triangles, and also 255 has nothing to add when all the points are on for this cube. And I always add this default here in case something happens and a case comes in that I didn't even think of, and it'll just tell me the error message. So this that first part that I just scrolled through, that just adds the vertices for the triangles. And remember I said to remember what the before count was? Now I'm going to find out just how many vertices that I add. So I subtract that from my before count, and now I know how many vertices I added. So now here, based on how many vertices I added, I have to have the same number of UVs. And since I did keep it simple that every triangle has its own vertices, I also have to have the same number of triangles that I add. Okay, so if I added one triangle, that's 3 vertices. All right, so added count's going to be 3. So for one triangle, I connect the 3 points in my triangles array. Bing, bang, boom. Right? I just take the count and just go back on the last 3 points added to the vertices, and that's my triangle. And then for the UV, this is where that UV coordinate thing helps me. You know, remember I think of that A, B, C, D, the corners of a picture. So for the first one, I just said A, D, C, imagining that triangle's like this. All right, now here I have 2 triangles, so I connect the vertices for the first triangle and the triangle array and the second triangle. And then I connect I specify the UV coordinates for the first triangle, A, D, C, and ABA is A, B, D, okay? Now, how many triangles did I have to add? At maximum, I found that I added 8 triangles, 9 triangles, 10, 11, 12, 13. Do you think I added 14? I think that's the highest one, 14, 15. 16 triangles, I think was a configuration I had. I needed to have 16 triangles at most that I added for a configuration. And this is how I knew if I needed another one, because I kind of didn't have a case statement. So I wound up with a configuration that needed 16 triangles to do the config. Okay, so that's what that does. So like I said, this isofaces function, this is the gold of my whole MarchingCube's algorithm, because this tells me how to draw the triangles inside a particular cube. And let me just use the outlining thing because I'm scrolling forever. Collapse the definitions. Yeah, so isofaces, this is the gold. This one, don't mess with it. So there's get cube config. Then if I pass in the config number, I could set the points. All right, so instead of going from telling it what the corners are, I could just pass in a number and it'll tell me which points are on. I could set the points on. That's just there for that. Oh, here's get mesh. Since you know, get mesh, it doesn't really have to do with the MarchingCube algorithm, but I just put it here because, hey, how am I going to create a procedural mesh without this function? So I pass in the game object, the empty game object, whatever, you know, and the material that I want to render on the mesh. And this get mesh function, it just gets the mesh filter component of my game object. If there is none, then it adds one, the mesh filter. And the mesh filter holds the mesh and all the mesh data, okay? Then there's a mesh renderer component. I get it. If there isn't a mesh renderer component on the game object, then it adds one. And the mesh renderer is responsible for drawing the mesh, you know, rendering the mesh and putting the material on it. So for the mesh renderer, that's where I set the material. That's why I passed in the material over here. And now finally, I got to deal with a mesh, right? So the mesh filter is where the mesh is. That's MF. So over here, I don't know if this is true or not, but I just found like when I'm in the editor, I had to use shared mesh. And when I was running the game, like if I compiled my game, if I built it, then I could just use mesh. If I'm wrong, somebody tell me. That's what I found out how to do. So anyway, if I'm running this project from the Unity editor, if I'm running the game from there, MF shared mesh. I see if I set that to my mesh. But if that wasn't allocated yet, if the mesh is null, well then, okay, I'll set the shared mesh equal to a new mesh, and I'll pass back mesh. This index format on the mesh object of the mesh filter, it is basically saying how many vertices can I add for one mesh. You know, the vertice count could go up pretty fast when you have a nice complex mesh, right? So by default, it's uint16, which is an unsigned integer, 16-bit. So a 16-bit number could only be having values from 0 to 65535. At least the unsigned it, because there's no negative values. So your whole range of values could go from 0 to 65535. Hey, I was playing around, and sometimes I hit that limit real easy. So what I did was I just kind of changed the mesh index format. There's another format you could do is unsigned int 32. So with unsigned int 32, hey, you can get like 4 billion. Okay, so that's like 2 to the power of 32. That's about 4 billion indices, and so far I haven't gotten close to that. But, you know, most of the time, if you do have something that's a really, really big mesh and you're trying to do it in a game, it's kind of unwieldy to put it all in one mesh. Usually you kind of like make little areas of chunks of meshes. You know, if you look at my voxel chunks. You just have chunks of areas, and they just match up together. Anyway, so that's what this index format does. It says how many vertices you could have per mesh. And, just for the heck of it, I give the mesh a name. So when you're looking at it in the Unity editor, it's going to have a name in the corner, right? And getMesh returns the mesh. So yeah, this isn't part of the MarchingCube algorithm, but hey, I need it. So I've had that. Then I have this function here called setMesh. And this is something that I pass it in the mesh object from my game object. And now it's going to take the arrays that were set, the vertices, triangles, and UV, set them on the mesh, recalculate the bounds of the mesh and the normals, and the mesh is ready to go. I think if you're using the universal render pipeline or the lightweight render pipeline, you also probably would need to call mesh dot recalculate tangents, okay? But each one of these recalculates takes time, so I don't add the recalculate tangents unless I need to. Okay, and that's what the setMesh function is. Now, I said I kind of had the thing here, Perler Noise in 3 dimensions. Yeah, because these are some YouTube videos. One of them's from Unity. This is where I found the way to do Perler Noise, which is a 2D thing, because you see it only takes X and a Y, and kind of turn it into a 3D algorithm. So Unity has math.f.Perler Noise, and that only works in 2D. But yeah, what I found was from these 2 YouTube video references is if I do this, first I get all 3 permutations of noise for X, Y, and Z, and their reverses, okay? So that's 6 permutations. Then I just add up all the permutations and get the average. Divide by 6, and hey, that gave me Perler Noise in 3D. So that worked. And you saw it work because it was in the examples. So I went through explaining the marching cubes thing. What's the time mark? 34. All right, so that's great. That's great. So I have the script here in my Unity project. Let me add an empty game object to be my procedural mesh. Create empty, and I'll just call this procedural mesh because this is where I'm going to do the MarchingCube algorithm. See, it starts off with nothing, and now I have to make a script that's actually going to create the procedural mesh for me. So let me do that. Procedural mesh, enter, and let me just drag and drop it to there. I'll do that again. Okay, I'm adding it to there. All right, now let's edit it. So here we go back. Got this out, get rid of this. So this is the minimal. Now I'm going to use that MarchingCube script to create a procedural mesh. All right, so this is the part where you have to write yourself. So let's see, first thing I want to know, I'll probably put it in the inspector window. It's going to be a vector 3, so I could get what the grid size is, like how big is this going to be. And I'll just give it a default value to, start off with 10, 5, 10, okay? Not 100, 10. Let's give it a default value to start off with. And then I need a material, right, to render on the mesh, so I'll let the user tell me. Material equals null, okay? So I need those 2 things from the user. Let me save, go back to Unity, and let it update right here. I'll just make this full screen. So I need a material. So let me get a texture from the internet. Boop, there's a nice texture, seamless. Well, those are rocks, really. And now let me make a material out of that. Material. And over here, I will pick that nice thing. And I'll enable GPU instancing. All right, so now I have a material. So let's give it to it. Oh, let me name it. Okay, let me name it rock. And then I will put it there. Okay, now my script has a material. Back to here. So when the game starts, void start. What do we want the script to do? First, I want it to make the grid. I have to have that grid of points. Then I want to add some noise to the grid so I could have points on or off in the grid. And then after that, go ahead, we're going to march the cubes. Okay, we're going to call a function called march. So now let me just skeleton out these 3 functions. Private void make grid. Boom. Then we have another one, private void noise. We'll do the 2D one first. And then we actually march the cubes to create the mesh. Void. And I'm just calling this function march, okay? All right, so in the make grid function, we're going to have to make a grid of points. They're going to be in 3D. So the first thing we should do is allocate that grid thing from the marching cube. So this is why I made MarchingCube static. It doesn't have to be, but I made it static, so I could just say MarchingCube.grid. So this is referring to my MarchingCube script, right? If I go to definition, boop, it's this guy. and it's these grid points here. Okay, I'm gonna go back to procedural mesh. So the Marching Cube grid, let me allocate it. Allocate the three-dimensional array of grid point. Okay, now grid point is a class I made too. If I go here to the definition of it, here in the Marching Cube, it has an example of a grid point class. I just need a property for the position and the on. Okay, that's all that's required. Okay, so this is how you do a property in C#. You say public, what's the type of the property? It's a vector 3, and the name of the property is position. Then you kind of put the curly braces. So now the property, you can get the value for which you return the value. So this is where I'm going to store my value. Or a person could say position equals, they could like be in their code and they type position equals, true, or I don't know, whatever, the vector 3, 0, whatever. So for that, you have to have a set part, and the set part, whatever they say after position equals, that's value. So here I just set my position equal to value x, y, and z. Okay, and on is even simpler. It's just a boolean. So return on, it's a boolean. And then when I set it, I just say on equals value. So this is the way you do properties. It's kind of like a function without the parentheses. And then inside you could have a get, and you could have a set component to it on the inside. You could have both of them, one of them, or the other one. It doesn't matter. Anyway, so for grid point, you need this. Okay, so you could use this one, which is the bare minimum, or you can make one. Okay, so we got a grid point. Let's make that a three-dimensional array. And how big is the array? It's going to be grid size dot x, grid size dot y, grid size dot z, x, y, z. Boom, boom. Now there's red squigglies because vector 3, these are floats. And when you're creating an array, it doesn't want floats, it wants integers. So we just typecast them as ints by putting in parentheses int in front of each of these floats, and C# will convert the float to an int. Okay. Then we're going to need to do so this part here was to allocate my array. Okay, so that's allocating. Now the second thing we're going to do is actually define the positions. Define the points. Okay, so we're going to use for loops, and we're going to use 3 for loops, one inside the other. So we're going to go through all the z's, all the z positions, grid size dot z, z plus plus. We're going to go through all the z positions, and inside that loop, we're going to go through all the y positions. This is going to go through all 3 dimensions. Grid size dot y, y plus plus, and the last dimension is x, x, y, z, x less than grid size dot x, x plus plus. Now let me make sure I got this right. I got z, y, and x. All right, I just wanted to make sure I didn't type x all over the place or one of the letters all over the place. All right, so now as I go through all 3 of these dimensions, the thing I want to do is I want to make the point. So MarchingCube dot grid at x, y, z. Okay, so for this position, I'm going to allocate a new grid point. So I allocated the array over here, but each position in the array is still null. So here, I have to, for this position in the array, I have to allocate a grid point class, okay? And then, for that position in the array, x, y, z, I have to set the position, and that is going to be equal to a new vector 3, x, y, z. So all my grid points are spaced apart by a unit of 1. So this works, okay? And then the last thing is I should say if I want the points to be on or off by default. So that is already covered inside the class over here, the grid point class. If I go to it, go to definition, you can see here that on is equal to false by default. So I don't have to do it, but just to be sure about it, because I don't know what somebody else is going to do if they use the grid point class or they make their own, equals false. So all the points are off by default. Okay, so this is going to just make a grid of points in 3D, and they're all off, all right? They're not really points that you're going to see in the scene. It's just a data representation, okay? So we have a make grid function, so that covers that, make grid. Now, all the points are off. We're going to use a noise 2D to turn some of the points on and make some hills, okay? So that brings us to our noise 2D method. So we have to loop through all our points again. So I'm going to make the loops again. So for int z equals 0 to until z, as long as z is less than grid size dot z, z plus plus. And this is a 2-dimensional, so for the loops, I'm only going to loop two times here, Z and then X. This is like the flat plane. You know, when you look at the Unity screen here, see these two things on the flat plane? That is Z blue and X red. That's Z and X. So over here, I'm just doing Z and X and looping across that equals 0, X less than grid size dot X, X plus plus. Okay, so for each of those positions, I want to figure out a noise to see if it's going to be on or off. So for, let's see, we're going to be using Unity's mathf.perlen noise function. And I spelled that wrong, but that corrected it. And we're going to have to pass in an X and a Y. All right, but in our case, it's an X and a Z. It's an X and a Z, okay? So the Perlen noise, it takes floats. The values that it's going to return are between 0 and 1. The values that Perlen noise returns are between 0 and 1. And the values that it wants have to be between 0 and 1. So X and Y here, they're going to be whole numbers. So somehow I have to have them as percentages instead. I have to have them as floats. So let me convert these to floats for X and Y, for X and Z, I mean. So I'm going to have an NX, float NX, the noise X value. And a way to do that is I just see what percentage along the X am I. So for my current X divided by the grid size X, and that kind of turns it into a percentage. How far along the X-axis am I? Right? Then I'll have a float NZ is going to do the same thing. Z divided by grid size dot Z. That's how far along the Z I am. And now here I could just say NX and NZ, and the values will be between 0 and 1. In other words, a percentage of the distance of my grid. So that will give me a value. What am I going to do with that value? It's going to give me back a float value. What I'm going to do with that is I'm going to determine how high in the Y column, how high up in the Y is this particular grid space going to go? How high is the hill going to go? So height, right? So that's going to give me a height. And what I'll do with that is for int Y equals 0 to Y less than grid size dot Y, I'll go through every position in Y in this column here. And if it's less than height, I'll turn it on. If it's higher than height, I'll leave it off. So MarchingCube.grid XYZ equals, oh, so this is a grid point thing, right? Yeah, this is going to be a grid point, right? So I have to set the on property. So on is going to equal true or false. So if Y is less than height, then that will be true. And if it's greater than height, it'll be false. So this is this kind of evaluates the true or false if Y is less than height or greater than height. Okay, so this is going to go through the Y column. And if it's lower than height, it's on. If it's greater than height, on is going to equal false. Boom, that should work. All right, let me just look at everything. Okay, so this makes the noise 2D. I think that's all I need right now because that's what I wanted to do, turn points on or off. See, so that's a noise 2D. We'll see how that works. Now for the third step here was March. So let's write the March function. This is easy. This is where we're going to use the MarchingCubes class a lot. So I need my game object, this game object, this dot game object, okay? And then what I'm going to do, first I have to get the mesh, right, with the get mesh function. So, I need a mesh variable over here since we're going to be making a mesh. This could be private, nothing for the user to mess around with in Unity. So mesh equals null. I always initialize everything. So here, mesh will equal MarchingCube.getMesh. And what does getMesh want? It wants the game object, so I have to say ref go. That's a reference to the game object. And it wants a ref to the material. So I kind of pass them in as a ref so that when getMesh is called, it's not making a copy and sending a copy. It goes a little bit faster if I send a ref. And then it directly affects everything for my game object when I send a ref instead of sending a copy. Okay, so that will get me a mesh. So then I want to do MarchingCube.clear just to make sure, clear anything I had from before, and I spelled that wrong. MarchingCube, I can't spell, .clear. That clears the vertices, triangles, and UV, remember. Now that the arrays are cleared, let's do MarchingCube dot march the cubes. This will instantly march all the cubes, okay? And that makes all the isofaces. It's a big deal. Then after that happens, now we could say MarchingCube dot set mesh. This is where it's going to take the vertices, triangles, and UV arrays and put them on our mesh. So set mesh and we're gonna put them on our mesh, okay? So that should do the march. I think this is bare minimum. Let's see what happens when we try to run this. So why did I do that? I could just leave it full screen. All right, so I save my code, and let's go to Unity, and everything, the script is on here. Now let me just turn Z this way, it's away from me. And now let me cross my fingers, file save, and let me press play and see if it works or not. Press play, and I see a mesh, and it's like totally flat. All right, so it did make a mesh, but I thought it would be a little bit more hilly. So let me see. Let's put a little gizmo here so I can see where the start is with a little insignia. And then we turn gizmos on. Okay, so we know that this is where the procedural mesh thing starts. It starts here and goes out. Now, let me just run this again because let me just take a look more closely. What happened? Did anything go up or down? No, everything is totally flat. That's not what I was expecting. I wanted some hills. So something is wrong with my noise function, I suspect. So let me take a closer look at it. NX, NZ to pass in the Perler Noise. Let's make this a little bit more complications in the algorithm here. Let me add a new value for the user to put in because maybe it's just that everything's too small. So public float. Let's add a zoom level for the Perlin. Okay, zoom. By default, we'll have it at 1, not 10, 1. Okay, and public. Well, let's do the zoom level only first. Okay, we got zoom level. All right. So how do we use the zoom level value? We're going to use it by taking this, and so we're not always between just 0 and 1. Then we're going to multiply by the zoom, so we could, like how far out or how close in. Just think of it like that. That's why I'm calling it zoom. This will make more hills or less hills. All right. And oh, I took this value for Perler Noise. It's literally between 0 and 1. Well, that's not enough because 0 and 1, that's never going to go up in the Y or down. That's always going to be between 0. That's always less than 1. That's why everything was flat. So here, let's multiply by our grid size dot y. All right, so we could have some height and stuff like that. Yeah, maybe that'll make a difference. I think this was what I was missing because this just gives a value between 0 and 1, but I need it to be just like I did these and I scaled them across. I need to scale the y between my heights. All right, let's save that and try that. See if that was really what it was. And that's what it was. See, because now we have a small hill height thing. And the marching cubes thing, you see it worked. These aren't cubes. These are triangles, and it's a little bit smoother than cubes. Okay, this is marching cubes. Now let's see the zoom thing that I put in. You saw how it looked when the zoom level was 1. Let me bring the zoom level up to 4. Okay, and now you'll see what I mean. It should have some more bumps to it. And yeah, it's way more bumpy. See, it's a lot more bumpy. Let's also test out that we could change the grid size. So let's change it to 80, 40, and 80. All right, let's see if we can get a bigger grid and see if that works. And it is bigger. There you go. It's really hilly. There you go. See, and if you look real close, that's the material that we set to render on each face. And these are triangles. Let me turn on the shaded wireframe. You can see all the different triangles that were made to make this. All right, so that's the 2D. Let's try a 3D algorithm for noise. So that's noise 2D. Let's make a 3D algorithm. Private void noise 3D. Let's fill it in 3D, which will make it, instead of hills, it'll look more like caves, okay? So let's think about that. We're going to have to loop through all 3 dimensions. So bear with me while I type this again, equals 0 to z less than grid size dot z, z plus plus, for int y equals 0 to y less than grid size dot y, y plus plus, and then the last dimension for int x equals 0, x less than grid size dot x, x plus plus. I got my 3 dimensions. Now the function that does the Perlin 3D, it's in my MarchingCubes class. You know, I added it here in the MarchingCubes class, and it's this one, Perler Noise 3D, and it just takes x, y, and z. So float, my noise value is going to equal MarchingCube.Perlin Noise 3D, and I just pass it x, y, and z. Now x, y, and z, do they also have to be values between 0 and 1? Yes, they do. So let's do the same thing we did with noise 2D and translate that into a percentage across our grid. So float nx will equal x divided by grid size dot x, okay, float. Oh, and we could also multiply it by zoom so we could get, you know, more complication or less. Float ny equals y divided by grid size dot y times zoom. And then float nz equals z divided by grid size dot z times zoom. Yeah, so this one's a little bit easier because I don't have to go through the y column making the heights. So now this is going to give me back values between 0 and 1, right? 0 and 1. How do I know if I want the point to be on or off? I guess I could just have like some kind of a limit to say whether I want on or off. So let's say here, let's give the user a chance to put in a noise limit for 3D. And for now, I'll just put it right in the middle, 0.5. Okay, so here what I'll say is the marching cube, the grid at x, y, and z, the on value is going to equal whether noise is greater than the noise limit. Okay, if it's greater, it's on. If it's less, then it's off. All right, let's do it like that, right? Save. Now this should be our 3D noise algorithm. So how do we use that? That's easy. Here in the start, we made noise 2D. So let's just comment that out and try the noise 3D. 3D. Okay, save it and let's try it out and see if we're lucky in the beginning or we have a mistake. So now I run this. And did it, what's going on? I don't see anything. Run it. Are there errors? No. Anything happen? No. Okay, let's see what's going on. Here, make noise 3D. Let's make sure it gets to here. Let me put a breakpoint here. Boom. Okay, and then let me attach that to Unity. So we'll hit the breakpoint. Now go to Unity and play. And we'll see if at least we get to our function. So we do. So let's see what's happening. XX, YY, ZZ. Let's see what comes down. 1, 2, 3. 0, 0. Oh, yeah, because I just started. Noise at 0, 0, 0. It's probably going to be 0. 0. Oh, no. 0.46. So 0.46, is that less than, is that greater than 5? No. So on should stay false. False. All right, so it is getting here. But there's nothing. So maybe I could put a breakpoint and see if the array of vertices and triangles is created. So let me go here in March. And just before I set the mesh, let me put a breakpoint and I can check to see if there's any vertices and stuff. Okay, let's start it over again. The code is still connected. It's still attached to Unity. I press play. And it's getting ready to run. Oh, I hit the breakpoint. Here we go. So Marching Cube. Let's look inside. Oh, there are no triangles, UVs, or vertices. Why? Why? Something's wrong with our noise thing because everything came out 0, I guess. What am I missing? What am I missing? X, Y, Z. Let me think. Okay, you guys probably saw it, but I just saw it. I just made these floats, an X and Y, Z. But here it's still passing in the ints. I must pass in floats, and X, and Y, and Z. I made the floats and then I didn't use them. That's what's wrong. I bet you that's it. So things like this happen. Now let me try running it again. And ta-da! I got it. I got 3D Perler Noise. See, I look at my wondrous caves, my caves of wonder in 3-dimensional space. And that's it for this tutorial. So the main thing is I created this MarchingCube script, and here I just showed you how you could use it in your games. Have fun. It's not optimized, but let's see how far you can get, and maybe I'll make another one because I know that the way these marching cubes were going, they just went on the halfway point, you know, between 2 corners. But there's another version where you could kind of smoothly go between the 2 corners, and then the mesh looks even smoother than this. So maybe that's what I'll do in my next video. See you next time. Thanks for being here. Bye. You made it to the end of the video. I'm so proud of you. This is my website. The main thing I want to show you is that for any of these videos that you've seen on YouTube, I have the tutorial section, which has the blue links for the projects, and the orange links are the files. Also, you could go over here and play some of the games we made in the game camp.